Thank you all for coming. So it's been 50 years since I've been involved in this. I worked at Westinghouse for 20 years, from 1960 to 1980. And I left at that time to go to Lehigh University in Bethlehem, Pennsylvania. And they had a chair in a position called the Sherman Fairchild Chair of Electrical Engineering. I went up there and stayed there 30 years. And during that period of time, though, that I was at Westinghouse, I took several years off, sort of took a mini sabbatical and came to Ohio State, studied graduate program in electrical engineering department. And back to Westinghouse again. And around 1980, I decided to go do some teaching at Lehigh University. I had been teaching part-time at the University of Maryland. Graduate students at one time, most of them come from various government agencies. So I like teaching, and also Westinghouse had a school of engineering and applied science at night, which is quite interesting. You join a company and then you go to school there and learn about what they're doing, different subjects that we involved. So that was like a learning experience for many of the people that joined. And there was a program called the Graduate Student Program. And what you did was you went around job to job throughout the company, going to various divisions, and hopefully you find a full-time job, and the agreement between you and the assignment. What I didn't realize until I was on my fourth or fifth assignment was that when you join the company on the graduate student program, that wasn't a job. That was an opportunity to find a job. And there were people that actually left the program after a while. One fellow went back to New York, worked in his dad's record shop. Things like that happened. And so we'd all get together at night and drink beer, talk about what opportunities we found. Well, I found a place down in Baltimore. There were a lot of electrical engineers, and I liked what they were doing. So I started working there around 1960. At that point in time, there was a program at that time that was involved with molecular electronics. And the idea was that you couldn't use capacitors, resistors, inductors, things like that to build a circuit. Using spins, fields, charges, waves, put these esoteric ideas together and make new types of circuits out of it. So it was this Air Force contract at that time. Meanwhile, while we were working on that, there was a fellow named Kilby, Jack Kilby, down at Texas Instruments in Texas. And he took a transistor and some resistors and put it together, and he made an oscillator capacitor. And we looked at that and we said, who can't do that? That's easy. But he got credit for developing the integrated circuit. So I think that will teach you, if you're working on something you think is crazy, just go ahead and do it. You may be the first to do something like that. So anyway, while I was working at Westinghouse, I started to work on vacuum tubes. That's all I studied when I was in college, vacuum tubes. I was in physics, but I took a lot of courses in electrical engineering. And vacuum tubes were what we studied. So I didn't know anything about transistors, except I took one course before I left the University of Michigan, my master's degree. That was on transistors. And it was taught not the electrical department, but in the metallurgical department. But I heard it was a good course. I went over and took the course, and I was hooked. I liked what I heard. I said, this is a field that I really would like to work in. This idea of making chips, small devices, studying their properties, learning the physics of these devices. So that was appealing to me. Marriage, physics, technology like chemistry, metallurgy, electrical engineering, systems types of work. So I found it when I went to Westinghouse. I found the company that I could work in the laboratory, make these chips, work with the systems people, find out who the applications were. That was very exciting, because often you work on something and you don't really see where it's going. Then to actually see where it's going, talk to the needs that people have, inspires you to keep looking in the air. So I want to talk to you initially here about some of the work that I was around that I was doing. I worked on vacuum tubes at the Westinghouse, but I was also working in a laboratory where people were making the camera. The camera was a very special camera. It was called the Lunar Excursion Module camera. It was meant for Neil Armstrong to take to the moon. Went to the moon, Buzz Aldrin, Michael, and they went there in 1969. So let me show you the history of imaging with vacuum tubes. I say that because imaging was done prior to about 1960 with vacuum tubes. Now, at the time that I was working with vacuum tubes at that time, this person here, Stan LeVar, was on the awarded to him because he's the project manager of the camera. He made it just 40 cameras to pick one to make it work well. And notice he's wearing, we call it a bunny suit. Nobody had worn a bunny suit before. They would all come in just like we are, sit down in the laboratory. Some people smoke, they put a cigarette out on an ashtray. There was no sense of cleanliness. Cleanliness was not needed to make chips. And you know, the most surprising thing, as I mentioned earlier, some of the people that were smoking and doing things like that were getting the best yields in the laboratory. So we could really figure it out. But anyway, Stan LeVar was the project manager, and he went out and got the award at that time. And this is the camera over here. Along with this camera, it needed 43 integrated circuits. But 19 of them we found weren't available. We had to make them in our laboratory. So I got involved a little bit in this area of making this. Now the camera was not transmitting at 30 frames per second. It was transmitting at about 10 frames per second. Because NASA, as I say here, studied system requirements from space and found that if you use a bandwidth about 500 kilohertz, that it reduced the power level down to the transmitters. And power was very important. You could not use much power when the Eagle landed from above the ship. You had to conserve all the power because you had to get that Eagle back up again. So it's very much important to transmit signals at low power. So the Apollo camera used 10 frames per second. It's called slow scan. 320 line scan format. So that if you go less than 15 frames per second, and people start walking fast, it breaks up the scene. But we didn't think they'd be running around that fast on the moon. And so we were able to get by. Now this is important to understand. How was imaging done on vacuum tubes? And the principle here is the principle of storage of information. It's something to keep in mind. So what happens is that we have a camera that's similar to this camera here. It's called a Vidicon. And so the electron beam comes out of the cathode, comes to the surface. Now what is this surface? The surface is a photoconductive film. Means that it's high resistance, but when light comes in, it can change the resistance of the film. Now, back of the film here, the conductive film, transparent, and connected to a resistor to a positive supply. So that whole back side of the film here, there's a glass plate positively charged. The beam lands on the surface, it scans back and forth. As the beam scans the surface of the field, under the beam area A, there's the resistance, and the resistance is the field times the thickness of the field divided by the cross section of the beam. That's the land approximately 10 microns. The capacitance of the film under that area is dielectric constant of the film. Dielectric times multiply these two together, you get the resistivity times the dielectric constant. That has to be high, much higher than you say it's a frame time. Time it takes for the beam to scan and come back. So when the beam comes back again, after bringing the surface to cathode potential, the backside is positive. If there's light on that surface, the electrons that are deposited will discharge. And the beam will have to supply those electrons. So the readout is done by a beam scanning the surface. Think then of the surface as being RC capacitors. And the resistor is light sensitive. So it's storing all the incoming photon flux. May have frame time. That's so important, that transfer storage. You can get the same transfer storage in a photodiode. Reverse bias it, and you have the back resistance, which is diode, space charge. Yes.
So people online are saying they can't hear very well.
Well, you can't. Can you hear better now online?
A little bit. It's good.
Is it better?
It's on. Yes, because it's a different audio. I think that's.
I'm talking pretty loud in the room right now.
Yeah.
Okay, I'll hold it up like that. I'm sure that will work better. Okay, so I was explaining to people in the classroom here or into the lecture room that electron beam is scanning a photoconductive surface, which is actually made up out of R and C, and that R and C exists under the beam diameter A. And if you look at the resistance under the beam diameter, and you look at the capacitance, the product is the resistivity of the film times the dielectric constant. That has to be high, and it's generally chosen so that it's much greater than the frame time. So what we did was we needed a lot of circuits. We needed about 19 circuits. Now nowadays you breadboard things, you buy them, and you breadboard them and see how they work. We didn't have programs like SPICE or Supreme to do simulations. But what we could do is we could design a chip that has a series of NPN transistors, resistors, capacitors, things like that, tapped resistors. We could do that, and then we could go in and submit the diagram as you see down here. And that diagram down here has the transistors, the resistors on there that are needed, and then it also has outputs coming to the pins that are shown up here in the package. So we would send this design to our wire bonding people, and they would bond up the array for us. And that's how we would test out the design. We do it on a chip, the bonded wire, not on a printed circuit board. Now, once we found a design that worked well, then we would design a photographic mask that would cover the interconnects instead of using bonded wire. So I show a picture of our chip here. This is a chip right here. We call it CLAM, Composite Lunar Excursion Module. Composite Lunar Excursion Module. So here's an example of a chip over here. We breadboarded this circuit. You can see that. We had a number of circuits that we had to build for the camera. Now these are the fellows that went to the moon, Neil Armstrong, Buzz Aldrin. were in the Eagle that landed on the moon, and in the main module, mothership, was Michael Collins. But here's a picture of Neil and Buzz coming back from the moon's surface to meet with the mothership. And this was taken by Michael as he's flying over the moon's surface. You can see over here, this is the Sea of Tranquility, and there's the Earth in the distance. Now, this is the plant that I worked at in Baltimore. This was called the Air Arms Division. We worked on things that connected with flight. The BWI airport, the Baltimore Washington Airport, is off to the left. And the surface division is over here. That dealt with the ships, radars for the ship. The main product at that time was radar, although that we had programs like the program that I showed to build cameras for the trip to the moon. And we also published a book at that time. All the authors got together. Here are all the authors. And we have our management team in here. Here's me, I'm a little taller at that time, off to the side, watching it. Now, I also gave a talk at a conference called NATO. And this was over in Europe and Belgium. It was a solid state imaging conference in 1975. And I worked with two professors, Professor Jespers and Van der Wielen at Louvain-la-Neuve. And here I am here. Notice the long sideburns. At that time, this was the time that we were all doing long sideburns and letting our hair grow. And this was the laboratory that we moved to from the Air Arms Division. It was called the Molecular Electronics Division. So this laboratory was built over here to supply commercial integrated circuits. It was the third leading supplier of integrated circuits in the United States at that time. But it kept losing people. They kept leaving, and the management kept leaving. Eventually, they had to close it down. So my manager over in the Air Arms Division and his manager, they decided, well, why don't we just buy that building and we'll transfer all of our work on integrated circuits over to the new laboratory. So they made a decision to do that. And the reason was that they saw that we could build these chips for the lunar camera. Why couldn't we build chips for the special products that the systems people needed and that they couldn't buy outside? So the idea was that we would be a supplier of advanced circuits and chips to our systems people. And our systems people worked in many different areas: radar, sonar, different areas, communication areas. And so they all had needs that we supplied these. Now, I mentioned before we had a night school in electrical engineering and in physics, chemistry. So I attended that, but I also gave a course in that. I gave a course in integrated circuits at the time. So I'm going to talk now about solid state imaging. While our laboratory was building a camera for Neil Armstrong to go to the moon, I was also working on what's called photodiode line arrays. These line arrays are used in satellites to do push broom technology. You can imagine if you're walking along with a broom and you're pushing it ahead of you. As the broom moves along, that's the satellite. If you imagine that you scan back and forth across the broom, you're scanning a line of photo elements at that time, particularly photodiodes. So that's called push broom technology. And one of the most important things there is to have a very low amount of noise in the system. Because when you get closer to the time that the sun is setting down, it's called a terminator on the surface of the planet. The variation in light level can be 100,000 to 1, 10 to the 5th to 1. So you need to have very low noise sensors. And at that time, our sensors were limited. Imagine a photodiode or a CCD can handle, for example, 200,000 electrons storage. That's the max. As you'll see later on, there's various noise sources, but the one that was the most important was the noise source that was connected with the the reset setting of the capacitor. And we had a reset switch that was connected to a capacitor. And every time you reset the capacitor, you would introduce noise. And I'm going to show you the principle of storage as it appears in terms of getting rid of that noise. So it occurred to me that the Nyquist noise, so I'll explain a little bit later, you probably know about this, but Nyquist noise is very difficult to measure. But if you take the noise and store it on the capacitor holds the result of that noise, especially if that noise is over a period of time and it's an integration process. So I'll explain that in a little while. So the following noise sources are really important in charge coupled devices and photodiodes. There's thermal noise, which is what I was just talking about, or reset noise. There's shot noise. Shot noise comes from electronics. These are electrons that float over an energy barrier. It all comes also from optical noise. When photons or photon excitation come from a scene, every time it hits, I say as a photoconductive film, semiconductor, you get an intermediate kind of shot effect. Tick, 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 tick. And it's creating electron hole pairs. And these are stored. So we store those. We don't know what they are from pixel time to next pixel time. We don't know what they are, but we can store them. And then once we store them, they're being stored on what we call a high impedance node. They don't disappear. We come back. And when we come back again, we're going to take a look at them again. But in the meantime, light has fallen. So we can subtract. If we take the first sample during the time that we reset, and the next time doing when we sample over there, I'll show you this. We can remove that noise. That was a big thing. Can you imagine if you store 200,000 electrons, and if that capacitance is like a quarter of a puff, 0.25 picofarads. 0.25 picofarads is something like about 200 electrons noise. So the top end is 200,000. The bottom end is 200. That's 1,000 to 1, or 60 dB. But people wanted to have 80 dB or higher dynamic range. How do you get there? You have to get rid of that noise. So people were not taking two samples, they were just taking one sample. So that's very important then to get rid of that. The other kind of noise is what's called flicker noise. Sometimes it's called pink noise or 1/f noise. And that's at very low frequencies. It occurs through surface and bulk traps in semiconductor. And then you have like fixed pattern noise. What is fixed pattern noise? Well, look at it this way. You have a vacuum tube. I mentioned that the beam scans a uniform sensor. When you go over to a solid state array, it's divided up like a checkerboard. Each one of those little squares is an individual sensor. And each one has a slightly different response, a different area, and a switch connected to it, which is different from pixel to pixel. We call that little square I mentioned in the checkerboard a pixel. So each one is different. So how do you get rid of the switching feed-throughs? And initially, when people try to make these arrays, the fixed pattern noise was terrible. Can you imagine looking at a scene and all you see are lines crossing up and down? It was terrible. And that's because you have not a uniform surface anymore and a perfect commutator like an electron beam, but you have a whole series of these switches. So we have to see if we can remove these, get a technique to do that. So that's what I started working on in the early 60s and into the 70s. How can we do that? Well, we're going to start way, way back over here with Max Planck. In 1900, Max Planck looked at the radiation from a cavity, a black body. And you probably have heard about this. And he found out you can get so many joules per cubic meter per micron over here. And there were constants involved that he didn't know what they were, C1 and C2. But he could fit the formula for this. And using Lagrange's law at increasing wavelengths and Einstein's postulate that radiation was caused by oscillators with photon radiation energy, which is basically some constant n times h nu, that's the photon energy, which can be written as hc over lambda. We found that analytically, C1 and C2 comes out to be this. So it looks like we're stuck here for a second. Trying to advance the slide. Going to the next one. Sorry about that. We'll get the slide going in a minute. Okay, so this is Planck's radiation law, and it shows you what happens to this body over here, h of lambda, with different temperatures. And 6,000 degrees Kelvin is a perfect black body of the sun. And this region over here is the visible region that's shaded. And what we did to characterize sensors was to integrate that law from 400 to 800, so a little further into the infrared. And if we do that, we get watts per meter squared. And these are the two limits. And the temperature is 6,000. Now, if you have a body that has it turns out, a conversion efficiency of 70%. That means 7 out of every 10 photons coming in, 7 of them get absorbed and 3 get reflected back. Let's see if this works. Okay, good. So we can calculate what's called the detector spectral responsivity, which is basically the charge times the efficiency times the area over the energy. And so this comes out to be picoamps per milliwatt per meter squared. And we can also take this and integrate this out and find out the effective responsibility over those responsivity over that wavelength. And I went ahead and did that here. So basically what I'm talking about is that the signal current that we're going to get out of the detector is the charge times the detector effective responsivity times this product, H effective. This should be H effective over here. I don't know, it didn't come out well. But this is the product of this is the exposure density. And that would be in microjoules per meter squared. So it's important to note that what happens is we characterize the input by an exposure density, and then this is the detector responsivity that multiplies that to give us the current. Now, the thermal noise here was developed by Harry Nyquist. And that's very important to understand this. Suppose we have a lossless transmission line with terminations of R in a load and at the source. So what's going to happen is that there's a couple of frequency modes, one in each direction, which are basically the velocity of propagation divided by the length. Now each mode follows Planck's law as a mean energy for this, HF over e to the HF over KT minus 1. And I don't know why these are not coming out on the machine there. But anyway, if you go down, if you go over here to low frequencies, the average at the mean energy is KT. So the mean energy on the line is 2 KT delta F. The energy in one direction, KT delta F. So the power radiated from one resistor will be absorbed by the other, and vice versa in the other resistor. And so we're going to have the power on the line, I squared R. This is the fluctuation in current. It's KT delta F, and since Bn is equal to In, that's 2R in two resistors, we have this formula. Now, I know you've all used that formula in the past. You've used that, but this is exactly how Harry derived it back in 1928. Now, what we do nowadays, though, is we take that noise and we basically integrate that over here with a capacitor. So this R represents the noisy resistor, but now in this representation, it's noiseless, and where's the noise? And so here we have the reset switch, and we reset the capacitor over there. This is what's happening. We reset the capacitor, we have to integrate that, and when we go through and integrate this, we get that the voltage that appears on the capacitor, the mean square voltage that appears on that, is KT over C. You see, the resistance is not in that formula. What we've done is integrate the noise out. So we've got the noise of KT over C, and we can say that the charge then is the square root of KTC, which is 400 times C at room temperature. So if I put a quarter of a picofarad in, like I said before, we're going to get something like 200 noise electrons. So that's that quarter of a picofarad. This turns out to be the capacitance that's at the input of the noise of the electrometer that's on the chip that's handling the signal out of the photodiode, out of the CCD device. So this reset noise, the key here is the reset noise is integrated, stored on C. That's a very important concept. So now we have that the noise current is 2Q I delta F. That's the average current I across the junction. That's shot noise. Now I is made up of leakage current that appears in the device plus the signal current. So as I mentioned before, this signal current is like a shot current coming in. And so if we go ahead and do a Fourier transform, multiply this by a square wave, we get the total noise charge now coming out is Q times I, mean value of the current, DC value of current, times exposure time. And so if you look at the charge, the mean square of the charge, part of it is due to photons, part of it is the leakage itself. And the effective energy over here is just the radiation times the exposure time. Now the other source of main noise is 1 over F noise in image sensors. And we can represent the resistor, and it's just represented this way, as 1 plus F0 over F. This is white noise over here, nothing to do with my name. It's just called white noise because it's not frequency dependent. And then it hits a certain point called the corner frequency. And that corner frequency is determined by the area of the device. Turns out that the more area of the device you have, the less noise, the less that corner frequency will be. You'll move close. But if you have a small area, that corner will move out. And in MOS devices, they being so small, you can find that corner about 500 kilohertz. It's out there. So this noise rises at 3 dB per octave or 1 over F. And sometimes it's called pink noise. So I mentioned that here. This is 1 over F noise. So the challenge in design of these sensor arrays is to remove the thermal noise, associated with the reset switch, suppress the shot noise due to generation and recombination at the bulk of the surface, filter the 1 over F noise, restore the system DC level, remove the fixed pattern noise, switch feed-throughs, variations of capacitance, and so on. And we're going to assume that the spectral responsivity and associated sensor quantum efficiency can be controlled by the fabrication process. Now I want to talk about correlated double sampling. This is my first attempt to look at correlated double sampling. I made a line array of CCD sensors over here, and this is the output circuit. So on a CCD device, you have one output circuit, which is shown here, that's collecting all the charge that's coming out, and then the processing is done like this. Goes through a preamp that's off chip. In my case, it was off chip. A clamp sample circuit off chip. An AD converter. Might have, for example, a transmitter or so. So this was a charge cover device with clocks. It comes to a collecting diode. Now you notice we have a collecting diode. This is P over N, which today it's N over P. We could not make devices on N-type, P-type surfaces because of the leakage currents that occur due to the fixed charge on the outside of the interface. So we had to switch over everything in the 60s to a N-type substrate. So then if you had positive charge on the outside, it would just cause accumulation of electrons in the surface, not inversion. If you had inversion, you'd be coupling one circuit to another circuit. So this was my first attempt to make the circuit, and the size of the sensors was 18 microns by 22 microns. These pictures are my first research out there. Now notice over here, this is the key in correlated double sampling. There are 4 processes going on at each pixel time. So we have over here one process which is resetting the capacitor at this point. Another process is turning on a clamp switch, reading that. The next process is to let the signal come into the capacitor. And then the last process is to sample at the output. And then you can see how beautiful the output sample looks. This is light coming in. I also made what's called a beamform. We're working with submarines, so it turns out it's good for beams. For beams, just to make a series of delay lines. So delay something like 8, 9, 10, all the way up, let's say, to 16. So there would be different delays, and then we would have taps on each of the delay lines. We would put weights on them and make what's called a longitudinal transversion fit. So get back to the readout circuit. This is the readout circuit. This is the same circuit. This part, a single picture of a photodiode. The difference is there's one of these at the output. This is the but in a photodiode, there's one of these at every point. So you can imagine the difficulty it was with photodiodes over there. They're all switching features. So what happens is, this is clear. You can see the reset operation. There's a little feed through here, and you clamp that up, you measure it. You measure it, you open the noise. Then over here, you let in the signal. There's no signal. Sample here. So when you sample, make a difference between the 7 and 6. Here it is again. Notice over here now, the signal is starting to come in. This. And then, so when you sample, so CBS correlated double sample circuit analysis. This is done by Bob Hansen. Just looking down the street from us. He basically said, well, that circuit that I have is basically looks like this. There's a diode, there's a set, and there's a sample. That's correct. This is correct. That's not the way he showed it. Paths. Notice this path over here. We have the same path going to the output. Path operation. The sample operation. In this case, right? It's different from the sample. So paths that take place at a degree of complexity. signal coming out, and one path was here, eventually together. So I mentioned here, plant sample traveling separate paths equals subtracting. But this technique is used with ABS. ABS means active pixel sense backwards. But it's different than the original invention. The paths are the same. But the reason that was changed was that if you keep the path the same, you ask the operational amplifiers to be used to respond quickly. At that time, you couldn't make op amps that respond very quickly. So, you see, we're always limited by the technology. So, anyway, here again, I want to take you through the 4 basic operations very quickly. This is what's called a reset operation. So, what you do is you have a capacitance that's over here. See, and you have a reset voltage. You turn on this switch and you set the node there to VR. And then you turn off the switch. So when you turn off the switch, there's a few. Measure that by turning on the clamp. So the clamp turns on and you measure what's on the gate. So let's suppose there's a certain voltage over here in VR, and there's a certain noise voltage that's been summed at that point. Then that voltage gets multiplied by GM. And the resistor over here, and it gives that point to GM times R times those voltages. It's stored on that capacitor. You close that switch, and this switch gets set to a voltage on this side. That's where your signal is that represents that point. Now it comes along and you turn on your what I call a mux. You allow your light level to come into that point. It takes a while to explain the CCD, all the storage is being done in the array, and at the output node, what you see is your sensor being fed into the output node. You only have one of these circuits, but in the actual photodiode array circuit, you have this at each location. So anyway, what's happening is that you allow the signal to come in. This is the signal coming. And then at the end of that period of time, we call it the mux. This is the mux time. At the end of that time, we sample and take the difference between that level and that level. Take the difference between that, remove the reset noise, filter what's called the one-ref noise. Why do we filter? Because it turns out that when doing a clamping and sampling, that in the time domain is like a filter. I'll show you that in a minute. So let's go over here and go through this clamp operation. The clamp operation is what I said. So that switch will clamp voltage at that point. And then let the signal come in. That's the signal's coming. Now what happens is the node at that point N looks like this. The voltage node is GM times RF. This is the signal that's come into the device over here. Plus the reset voltage plus that noise. And you subtract out the clamp. Clamp is VR plus VN. That's the first one. And it's holding at that. And when you subtract that out, you get a nice clean signal. You don't know what that noise is. You don't know what it is. It's barely from pixel to pixel. It's the faint time fit. But you don't have to know it. You just sum it up and hold it. And then subtract it out. So that's the beauty of this technique. Most techniques are kind of simple when you think about it. Like, I don't know that noise, but I'm going to sample it and hold it. And I'm going to keep it for a while, and I'm going to come back in difference. So, here is the sample part, and I'm called lead signal. So I put a patent in the patent. It was reissued in '79. We found some things that could apply in other areas. Now, you know, correlated double sampling. it's not just for imaging. I decided to concentrate on that, but it really is used in signal processing generally. It's used in all kinds of switch capacitor circuits, A to D converters, modems, you name it. It's used everywhere to remove noise once you're resetting something, and to remove switching feed-throughs. Without CDS, you would not be able to get a photodiode imaging array that looked good. So what the fixed pattern will kill you. Imagine you have to make every one of those picture elements the same, along with the switches. You can't do that. I mean, it's even your best processing. So anyway, I won't spend a lot of time on this, but basically, I sort of mentioned already that you have traditional photodiodes and CMOS technology, and you have CCDs and CMOS over here. So I borrowed these from the literature. And you have two different ways that CCD works. You can image in one section and then move the whole frame over and storage it over here. You can do interline. In other words, you can image, transfer to a readout register, so you can have these registers read out, and you have a mask over them. So here's the basic circuit that's used at each location of the photodiode. It's the transistor, reset transistor, the photodiode itself, and the amplifier. That's so basic. Reset, photodiode, amplifier. And then you have a switch over here. This is the row switch. We're doing rows. You have a column line. So this is here it is again, the basic device. There's been variations in this. This is the basic cell. Here I am over here, a little taller here. This is my medium. This is management of advanced technology. That's been this, that's the head of the division. So give me a patent. You get so many patents. Stand around, take a picture. Notice I'm not wearing the same kind of suits and everything. You can tell who the engineer is. So let's talk about how to analyze. I'm sorry I drew this because I didn't know any other way to do it right now. Basically, you're putting in a certain amount of exposure energy. So detector, you create signal charge. But in the process back here, that node, before it gets processed, you have noise. Now you have that analog signal processor. Then you have A/B bits, and then they come out with bits. And here's what we do. We put a certain amount of light in, with wavelength, and we measure the number of bits. And we vary the intensity of that number. So then we have a plot of A to D bits on the vertical, we have on the horizontal, we have variations in the effect that would be in so many microjoules per meter. Energy density. We make a plot of that. Now there's a line that comes up like this. If we take the inverse slope of that, delta BF divided by delta A bits, that's called quantizing. So it would be so many microjoules per meter per bit. Now, when we take samples over here, we take 1,000 samples for each one, at each level, 1,000. So we take 1,000 samples and measure the effective energy and the AV bits associated. We take the mean value, that gives us the quantized. But we take over 1,000 samples, we can find the variance. Each sample will vary slightly. So around that line that I mentioned, we'll have a variation back and forth on that line. That's the noise. That's the total noise that we're getting. And part of it, noise, is due to the shock noise of the radiation coming in. Now you can just imagine, if we keep increasing the radiation level with the input, eventually it gets so large that it's dominant. So we can measure at very high radiation levels, it turns out, the responsivity of each detector element. We can measure that. So I want to show you the circuit then. This is the circuit. This is, you've seen that circuit. And I put a resistor. This is at the output of the CCD. And then we have this preamp. Notice it has now a filtering capacitance. This is the clamp circuit, where we clamp it. This is the sample circuit. And we have an output amp, buffer amp. So this is called a gated integrator. This is called a clamp sample technique. These are the four waveforms. So this is a pixel element time, T. In that period of time, we have four operations. We reset. We measure the value of that reset. It's called a clamp. We allow the signal to come in during that period. We call that the mux. And then we sample the output right over here. And when that sample is taken, it differences automatically with the clamp. Beautiful process. So this is the preamp. This is the clamp sample represented by a delta function here, and simply by a delayed delta function here. Tau 0 is the exposure time. So we get the total transfer function. If you put this together and you put J omega in, you'll see you get a sine squared. And that's that thing here. Now it actually looks like this. Comes up to the same height. But it rolls off due to the preamp. Rolls it off. So what we're doing with this process, we're removing KTC noise. We took away those 200 electrons I talked about each time at each picture element. And we suppress the 1/2 noise. Now, how do we suppress the 1/2 noise? Well, this is just a repeat of what I said before. This is, I'm using here white noise. White noise is a constant noise. So if we, in our transfer function, if we have a constant noise, then we're just going to get the bandwidth of the thing. Comes out to be the integration of this. And we're just going to get something like this for the total charge. This. And we've done some work at OSU here to look at spectral noise current intensity, and we find out that coming out of a MOSFET to the front end, there is a dependency on what's called remote Coulomb scattering. In other words, if you have charges that are in the oxide, they will scatter the electrons. And over here, if you have surface roughness, that will do it too. And this is the mobility. So I don't want to go into that. This is the density of traps at the surface. But when you look at the whole thing, it looks like this. The noise coming out of the MOS electrometer can be converted to current using this. And then we get 4 kT, 2/3 over GM. So if you look at some books by Rizali, for example, he will talk about that. But he won't have any knowledge of doing this over here. But the interface trap density is very, very important. So that's why it's important to study how to get interface trap densities down. And eventually the charge that gets reflected at the gate due to all these processes is the current, noise current spectral density in the MOSFET times the effective bandwidth over C over GM. And this bandwidth over here contains a part which is resistive and 1/F. So maybe you have access to these things that I'm presenting. So basically, I have a 1/f and a thermal noise, and I went ahead and did that. Now the thing with the 1/f is you're going to have a pole that looks down here like this. So you can see that it gives, I thought it was going to give me a lot of trouble to do integration, but my math can't integrate this formula out. So the next slide over here, I took, this is just a repeat, I took, and this is the constant resistance bandwidth times, it's the constant bandwidth times y. Y is the amplifier bandwidth times the exposure time. So I don't expect you to follow all this, but you can actually model the bandwidths for the graph noise and the thermal noise. So the one thing I want to mention then is that if you take the total noise, if you take the total noise and refer it to the gate of an MOS transistor, that's where we refer all noise to the gate of the MOS transistor of the electron. So that noise is the Nyquist noise, which is KTC. The shot noise, which is two types of noise, leakage current and photon shot noise, and generation recombination amplifier noise, noise plus any resistance associated with the electron. So that's electron noise. Now there's four other noises I have to include. This is not really the total at this point. What I have to do is talk about the quantizing noise, so that if you vary, for example, if the error between one quantizing interval and another goes linearly as m times t, then you just take and integrate that, average it out, find the mean square value. It comes out to be qi squared over 12. So as I mentioned before, you put exposure energy into the detector. It gives you a signal coming out. So RD times this. You process it over here, you get so many inputs out here. So here is your line. You slope that. It's quantized. And then the variation of 1,000 samples will give us the noise. So the noise at this point consists of these terms. External noise, which I can put it like that. ATC noise, leakage shot noise, runover noise, shot noise due to the photon storm, and quantized noise. Now you see there's a lot of noises over here. But what CDS does is it removes this noise. Then it can be a dominant noise, especially at low light levels. It kind of suppresses one of the breath noise. One thing I want to mention to you is that going back over here, one of the breath noise, C comes down is F squared. It's going down is F squared. Noise is going up is 1 over F. So at very low frequencies, one of the breath noise is canceled. Very low frequencies. That's beautiful. So anyway, this is the total noise, and then I did that example here. If you take the total noise, measure is a function over here of the measure is a function of the exposure density. You can see over here that the ideal would be this. Ideal means the noise only depends upon the light level coming in, fluctuations in the photons. But that's unrealistic. And you don't get to that level unless you get the high exposure densities. And then the slope of the line becomes Q over RD. And you know what these values are. So my goodness, you can determine detector responsivity. It each detector. It's pretty cool. So the slope at high densities gives detector responsivity. And now the chip noise, which is down here, is the measure. That. And this is still present over here. But this is still, here I put it in terms of voltage instead of current. Flip back and forth. But here's the total noise again. It's Nyquist noise, we said. Nyquist noise, photon shock noise, electrometer noise, quantizing noise. And then what we do is we set the signal to noise equal to 1. Solve for EF, that would be the noise equivalent signal. That's how we do it analytically. So now, these are the applications of CBS. Over 6 billion cameras today use CBS. Cell phones, television cameras use it. Underwater photography, sports, science, can exchange with. Some people are north of London is the project manager. And that's how we use it. Drones, you've seen that in Ukraine. Satellites, defenses. Digital photography in a row. Take pictures inside your mouth. And then endoscopy. There is an amazing number of applications. I'm sure I missed some. So, in summary, correlated double sampling is many applications. What can I say? It extends the dynamic range of the sensor, reaching the width. That's background and the image. That's the best you can get. To see the fluctuations in the background photons coming in. CBS method is used in other signal processing, such as switch caps, which replace resistors in integrated circuits. So now, I'm going to take you to the end. 50 years after that, imagine getting a telephone call, and the telephone call said, we're going to give you an image, and the committee in New York has recommended that. But we want to know, did you work at a company? And I said, yeah, I worked at Westinghouse. And he said, well, we should give one to Westinghouse too. I said, well, they don't own the company anymore. They said, who does? I said, Northrop Grumman. Well, give it to them. So they came with me to this fair out in Las Vegas. It was kind of like at the tail end of the pandemic. I was moving out. So this was here's the image statuette. It was designed by an engineer who said he used his wife in the model. The statuette depicts a ring woman holding an atom with spinning electrons. That's not a globe, it's an atom. And so the first engineer in 1949. Because in 1949 we were getting introduced at that time to black and white TV. And it was wonderful. The people said, we ought to give an award to that. Now the technicians at that time, they would work with the image orthograph, which I showed the picture. They would call that Emmys. They said, we don't want to use the name Emmy. We want a woman, so we're going to call it Emmy. So that's where the name came from. The first award was an engineer. Everybody liked it. Actors wanted it too. So it started giving to a lot of people. And when my wife tells people that I want an Emmy, they go, what? How could that be? How could it? You know, he's not doing any acting. Maybe doing acting, but not what they think. So anyway, it's given to people they call the tool makers of industry, people who make things for television that are important in television and imaging. So I have some notes on that. Maybe you'll get this. OSU had a little drill on me too. In the award. I think I probably own like your OSU Scotland. I'm kidding. I mean, what do you get in for an engineering teacher? So, anyway, here I am out there. That's my son's off to the left, holding the statue. I think you'd be interested in this. Yes, sound.
Yeah.
This is a company that's based in Chicago. They make cameras. They have been making cameras since the 1930s. And they have the same molds that they use in water screws. So I thought it would be interesting. It's a short video that shows you how they make an amp. At least when I did a dry run.
One of the exciting things here at RSONs is the traditional craftsmanship, the Americana way of doing things, the old school way, and continuing to use some of the equipment that was designed and utilized from the 30s and 40s, the golden years where everything was made entirely by hand. Our mold library dates back to 1938, and we're proud today to be able to use the same molds and the same equipment that we've used in some cases for up to 75 years. We at RSONs have been fortunate enough to be able to create the Emmys for the last 38 years. We've made them all entirely by hand, starting with virgin metal. Our virgin metal is heated in our furnaces at approximately 700 degrees. From there, our operator will then ladle the metal into one of our steel molds. Once the casting cures for approximately 20 to 30 seconds, it's solid enough to be able to be removed from the mold. After the casting process, the first step is you have to remove the gate which allows the molten metal to enter the mold. Once the gate is cut off, there's a lot of excess flash that needs to be removed in order to bring the details of the statue to life. That's done in the deburring department where they grind and deburr each of these entirely by hand. After the first steps of polishing have been completed, it's time to add the famous Emmy neutron ball. Each neutron ball is soldered together by hand, consisting of 6 pieces. It goes from that stage to the electroplating department. Electroplating was originally intended strictly for anti-corrosive properties, but it was then learned in the late 20s and 30s it could be used for decorative purposes as well. The series of alloys that are applied to Emmy start with zinc, and then it goes to copper, nickel, pure silver, and finally, a nice layer of 24 karat gold. An Emmy becomes personal once it belongs to somebody. That happens in the engraving department. The information is sent to us from the Television Academy. We produce plates for every single nominee because nobody knows who's going to be the final winner of a Television Academy Award. After all of the components to produce an Emmy have been quality control checked and approved, they get sent individually to the assembly department, at which point they are all assembled and put together. After she's assembled and quality control checked for the final time, she is then placed in a box designed specifically for her and then wrapped and shipped to the event. It's really exciting to work at an organization that still has the opportunity to produce things made by hand by Americans the old-fashioned way, and that's with grit, hard work, and sense of quality.
Well, it's not every day that you get an Emmy. I thought you'd be excited to see that. So what I found out was that they were interested actually in giving it to companies. They wanted companies to buy a lot of those Emmys, and so it's pretty amazing though. We go out there and apparently do this every year for an awful lot of people. They have Emmys in different fields, as you might guess, and they have a panel of people sit around. There must be 24 people in the panel, and then there's sub panels. There's a lot of work that's put into
going over things. And so it turns out that I think the previous year or 2 years ago, Eric Fossum, who I mentioned here, he's I think he's the provost of Dartmouth University now, but he still does work on imaging, and he won an Emmy.
It's quite an exciting thing. And oh, by the way, I have this slide here too. The students that came out, much older now, and other families, and they just showed up. I didn't know they were coming. There's a moral of the story that takes 50 years. So I mean, you hear about all these people that work for 50 years. It's a long time. But sometimes it takes a long time. We started working on imaging devices. We started working on imaging devices in the early 60s. And it wasn't really until about 30 years later that they became affordable, practical, a lot of the problems solved really in manufacturing. It's not easy to get technology out there and satisfy people and be inexpensive enough. I heard a talk one time from Sony, an executive there, and he said that they spent 20 years working on DVDs. 20 years. They said they could make a DVD in about 20, in the first couple of years. But he said that it would be $20,000 if we tried to sell this. He says that we spent all that time working with so many people to try to bring the cost down. And then I worked a little bit, I still work a little bit with NRL, Naval Research Labs. And they did a study, and they found out at 14 and 15, after an invention, after you discover something, it takes about 15 years to even think about getting it out into the public. Because you've got to go through some trials, and you've got to make sure it's going to go out and be handled by men and women in the field that is safe. And there's so many things that go into a product. That's why you read on Google all these wonderful things that are happening. But I tell you, it'll take a long time to actually make something work well and manufacture it. And anybody who's ever worked in industry, and many professors haven't worked in industry, they will see how difficult it is to make something, how difficult the job is, and to solve the problems. It's not easy to do. So you can come up with things, but then can you make more than one? Can you make thousands of them? And you say, well, that doesn't matter. We showed that it can be done. In engineering, we have a different way of looking at it. So anyway, I appreciate you all coming. I know I ran over time. That's the mark of a professor, I guess. He just keeps talking and talking. And but if you have some questions, if you're thinking about some things, I'd be glad to handle them. And not too technical now. And I hope the society gets going here real well in Columbus, the Circuits and Systems Society. I told them when I first came here, I said I started a society in Baltimore, Maryland. And we went to our first meeting, and we had advertised it and everything, and we had a speaker there. I went with the speaker, and nobody showed up. And we're sitting there waiting down in Baltimore, and this guy comes into the room, and he's got old clothes on, and he's got a broom. He said he was there, he's going to clean things up. And he says, what are you guys doing here? And we said, we have a meeting. He said, can I sit in on it? I said, yeah. So we went in,
and gave the talk, and it was just one fellow who came into the room. So that was my experience with trying to get something going. But it was it was very interesting. So thanks for coming tonight. Thank you. Thanks for being online too, all of you. You're still staying online. Sorry that I kept holding the mic in and out like that, and the volume wasn't good enough. But I think you'll get a copy of it, so you can look at it and see my errors in the slides and things. I spent a lot of time on those slides, believe it or not. I think they still have some errors. So thanks again.
Questions from anybody online?
Any questions, as long as they're not too hard.
I'll ask one. Thanks, Mark, for a wonderful presentation. Did that camera that Neil Armstrong took, did it work?
What, Anand?
Did the camera work that Neil Armstrong took?
Yeah, it worked, but we told him not to point it at the sun. And guess what? It burned a hole in the retina. No, it worked all right. I think they had to leave it there, though. You know, they had to get rid of all weight, excess weight they didn't need.
Oh, so he didn't bring it back.
Well, we had models of it here. I have a model of Stan Labarre when he was old. A picture. There's a lot of things I left out here that it seemed a little corny, but Stan was happy. When he got the award, there was the actresses around him. You know, very famous actresses. I didn't have any. I had some guy that played the piano or something like that. But it was a lot of fun. And got a chance to meet, see, I'm from New York, from the Bronx. And I got a chance to meet the guy that was head of the committee. He's from Brooklyn. So we kind of had a good laugh. And anyway, it was a long time, 50 years. When I left Westinghouse in 1980, I never did any work on CBS, never. I did some consulting work for Kodak. You know, I'll tell you a funny story, if you want to hear a really funny story. In CCDs, they have something that's very unique. I'll tell you what. So I did some consulting, and one time they built a CCD array, and it wasn't working. They thought I was a miracle guy. They called me in the laboratory. You know, consultants don't usually do anything. They just get paid for their resume. So I went in there and took a look at it, and nothing was coming out, no picture or anything. So it was a surface channel CCD. That meant that the carriers moved along the surface, but interacted with traps, so that you were losing a lot of carriers before it got to the output. We had a solution for that for people working in the field. I asked them, I said, did you put in a fat zero? And they said, what's the fat zero? Well, that's a bias charge. It's a DC level charge that constantly flows through CCD, and it fills all the trap levels up. And then the signal sits up on top of that like an AC signal. And you can see that then. And so I said that you have to put in a bias charge. I said, that's a fat zero. So I went to lunch and I came back, and he was screaming and happy and everything. And the picture was on the screen up there, it was working. But I know the feeling, you know, when something works. I mean, we've had periods like that where things just didn't work at all, and then suddenly they work. So they thought it was really, that made I was hired on at that point. I was asked to come back a number of times. They listened to me when I talked now. They thought, well, he's going to send us some interesting, information and help us. But that was the most interesting information I gave them. But I just happened to luck it out. and asked them if they put a fat zero. But I kind of figured that they weren't because, if you put a fat zero in, it would fill all those interface traps, and then they should be able to see something. They weren't seeing anything. So that was really good. And but Kodak made the first imager, first big imager with CCDs, first one, like a megapixel imager. Many people don't know that. They built also the imagers that went to Mars landing. So they had a very good imaging division, but like companies don't invest in some of their products, and they just I don't know, they fell behind. But they were pretty good. So I used to give short courses with some of their people, go around and give short courses on how CCDs, photodiodes worked. I mean, I could have kept going in photodiodes, but I thought these are really better. They cost more. There's no question they cost more. But what they offer is that there's no switching transistor in each picture. So that's one thing. And you get less fixed pattern noise to try to remove. That makes a nice looking scene. And I like that, I mean, for astronomy, imaging, can you imagine in astronomy what you do? Like on the James Webb, they cool down to 6 degrees Kelvin. 6 degrees Kelvin, and they're using an arsenic doped silicon substrate. Arsenic sets a small level, about 50 millivolts below the edge of the conduction band. And so if you look at a photon coming in and it hits an electron at that level and it bounces up into the conduction band, that's how you get your carrier. And so that 50 millielectron level gets you out to about 30 microns of infrared. Now, the reason that they have to use infrared is that the light that's being emitted are coming from transitions in hydrogen. But that's 13.6 billion light years away. And when that transition occurs, it's in the ultraviolet region. But because the universe is expanding, the wavelength of that light gets longer as it moves along. So it starts out in the ultraviolet, and then after a while, it's moved to the visible, it moves to the near infrared. It's all the way out from the ultraviolet to close to 30 microns. The Hubble can't see that. Can't do that. But the James Webb has that capability. It's absolutely amazing. They can see in the Webb galaxies formed at 300 million years from the so-called Big Bang. Do you realize that there should be no galaxies there? There should be nothing but hot plasma. Yet they're seeing galaxies. It's upset the whole cosmological thinking. Think about that. Yeah, question, Sam.
We have a comment online from Dennis Adams.
Oh, yes, Dennis.
So he says, an honor and a privilege to have worked with Marv since 1976. He has remained a valuable member and founding father to our foundry in Baltimore. He supported our programs for over 45 years after leaving for academia. His contributions played a key role in our systems that used imaging techniques to keep our nation safe. Cheers to the brightest guy I ever met in the semiconductor industry, and glad he did not wear his suit coat from the 70s to the MBA Awards.
I did not pay him to. No, but Dennis and I have worked together. Can you imagine? He was still working there until this last year. And then he retired. And now he's championing the bid to get back as a consultant or to work with him again. You know what Dennis says? He says the young engineers today, they just don't want to put the time in to learn these things. And so he's accumulated this knowledge over the years. And he gives them tests in the industry. He tells them, to solve problems. And then he comes back after a while and checks them. So he's really good. He could be a good educator. But basically, it's a problem solver. He solves problems. Taufik, thank you.
That's as quick as I took that.
Yeah, you know, it's hard to talk about a lot of your work, Dennis. And you know, you don't know if who's listening. So I just try to keep it pretty general.
Any more questions from in the room?
Yeah.
Yeah, I was wondering, like, some inventions come from just like sort of like trial and error, and you try a little thing and it gets a little better, and others come in like a sort of flash of inspiration after you've been working on a problem for a while. I was wondering if you could speak a little bit towards like when you first sort of like came across this circuit design. Was it more one or the other, or sort of what was the moment where you're like, I think this will work?
Well, I looked at what is the basic thing that's done in imaging? It's to have storage, to store a signal over a period of time. In the case of vacuum tubes, we say a frame time, and it's a exposure time. You know, the arrays that we're dealing with, CCDs and photodiodes. So if you're storing information over that time, how are you reading it out? That's the key. And so before you put the information in, allow it to come in, you have to prepare a place for the information to go. And what we were preparing it for was to hit a capacitor, to store on a capacitor. That capacitor has to be reset, has to be stored, a voltage has to be put on it. But you can't put a voltage on anything without introducing noise. Now the noise can come from the Nyquist noise, the fluctuation of electrons. It can also come from bad filtering, from the voltage that's used to, you know, that you're using for a reset voltage. And we try to use batteries for some of the things, but it's many people don't know how to filter right. Power supplies, they think it's a kind of a, you know, just a game to do that. But if you're worried about low signal levels, low current levels, you got to filter everything. And it's not easy to get rid of noise. So I was thinking about how do you get rid of noise? So I was thinking that if you take this Nyquist noise and sample something, like sample the voltage, you can put the voltage on there, but then what's going to happen? You've got this noise that went on across the capacitor, plus you've also got feed-throughs from the switch that you used. So you've got all that stuff happening. And but it's there on top of the capacitor. You don't know what any of it is, but it's there. So that once it's there, on top of that, you put your signal on top of all that stuff you don't know. But then if you wait a period of time and that the signal and the especially the stuff that you did initially stays there, it doesn't decay, because it's what we call high impedance node, it just doesn't leak away. Then if you sample them again, in this particular technique, it removes that uncertainty. The uncertainty of bad filtering, and you know, because everything is, you don't know what it is, but it's just sitting there holding. In fact, you read it once, and by reading it, means the effect of that produces a current, goes across the feedback resistor there, stored outside of the circuit plant. Then you do the same sample, and in the sample process, you're going through the same event, through the electrometer, you know, all of that. So the paths are pretty much the same. And the first time you see that, you actually go around the screen, you see how clean the signal is. I said to somebody earlier is that if I reverse the clamp of the sample, all of a sudden the A-scope will jump up and down, back, up and down. Then if I put them in the right order, clamp, sample, not sample, clamp, you know, it's made all the difference. It looks beautiful.
those are all Java units, something like that. You see that, this is eye opener. So you have to do a little thinking first. You have to think about what you want to do. What's the limitation that you have? You were with a customer, we were getting a certain amount of voice equivalent signal. So I don't like that. I want to see something that is much lower than that. So we were able to reduce the numbers back to 10. I mean, that was just incredible. And the other thing that we were able to do, though, is bring in money. Suddenly poured lots of money in. So there's a lot of things that are possible, you don't realize it. And we started with a 50,000 contract. And it literally grew. And it built buildings, facilities. So it wasn't just that. We worked with non-dominant members. I looked at members. They each part. That was members. Why did they go up there? You could buy those members. Everybody else was making them. Our members were radiation hard. So we don't have problems in the earth. Have problems up in space. It's highly radioactive. So our devices can take radiation. Very, very good. So that's the other thing. These are up there. They store the information to move the mirrors. Mirrors had to all be aligned. Mirrors. Dennis probably can talk more about that. It's really amazing what you can do with advanced technology. Working on all kinds of interesting things. And if you have the systems people that can use them. So one problem going to work in the state, one problem working in industry that's related to making of chips is all you do is make the chips. That's good. But the satisfaction I would get out of making things and not seeing where they were going and used. Now, Anand actually takes the students that he's working with, and they do internships. So sometimes they can see where they're being used and the results of research. But that is really impressive to me. I was not really able to do that where I worked, but he's able to do that because he knows so many people in industry. I didn't know too many. And the only industries I knew, you needed clearance. So anyway, but it's been nice coming here and talking to you all. I hope you stay with the Circuits and Systems Society. It's very, very good. And we do need to have circuit designers. Right? We get hire more professors in this area and people who are interested in circuits and systems.